I work at EPFL. I'm a PhD student actually at EPFL. And I'm going to present to you some of my most recent work on the selection effects on cosmic void BAO. The idea being that if we want to improve cosmological constraints by using void information, we should know how to differentiate what is actually empty in the matter field, that is what's actually a void, versus what is incomplete because we just couldn't observe it well, right? Which is pretty common in Redshift surveys. So here you can see all my collaborators, and let's just dive right in. So a brief, very quick introduction into Byron Acoustic Oscillations, or BAO. It's a standard ruler, right? It's a distance you can measure at various different redshifts, and then you can use it to basically reconstruct the expansion of the universe. And you can see here, for instance, what you do is you have different tracers and you compute the 2-point correlation function. And then you measure at which separation this peak, this BAO signal is. And then you do that for these all different shells of redshifts. And then you can build this expansion of the universe history. So this is normally done with matter tracers that you observe in surveys such as EBOS, which it made this wonderful plot. And then you take all those measurements and you can use them to constrain your cosmological parameters, your abundance, your density parameters, as you can see here. So what we want to do now is to use void information in addition to the galaxy or the matter tracer information, the 2-point information that is currently used. So what we will say are cosmic voids are, well, is in line with the normal definition of underdensities of the matter field, right? But when you define it, it becomes a bit more difficult to define them in a more general sense when you want to compute them. So we take a very simple geometrical definition, which is, voids are a subset of the circumspheres of the Delaunay triangulation simplices of the point set. As you can see on the right, a point set can be divided in this Delaunay triangulation, which has these simplices, and each simplex has a sphere, a circumsphere associated. We say those are our DT spheres. Now you can see here that you can find spheres in the overdense regions, right? So these actually are not cosmic voids because they don't trace underdensities of the field. However, the large voids do trace the underdensities of the field, right? So the issue now is, how do we define small and large, right? How small is small, how large is large. To do this tessellation and extract void catalogs from the point set, we use the now public dive and PyDive codes you may find. So the issue is that this geometrical definition is quite unable by itself to differentiate real voids from unobserved regions, right? So it has also been shown that the cosmic voids, when combined with galaxies, they yield a roughly 10% improvement on the error in the measurement of the BAO scale, which is roughly a 20% surface size increase, which is quite a lot, especially as surveys get larger and larger. So this was done on BOS. A paper we will release in the coming days is concerned with EBOS. And then DESI will be the biggest one yet, so we're looking forward to that. And the interesting thing about these voids is that if you extract them from the point set, you can find them at different redshifts, right? So you can build this same ladder by combining their information with the galaxies. And it's basically information that you already have. You only have to know how to deal with it now and how to extract it correctly. You can see here some galaxy correlation functions, void correlation functions, and the combination of them both, which is actually used to measure the BAO scale. So what's the motivation for this work? Is that the voids basically depend a lot on the tracer density, as you can imagine. So here you may find the void size functions for different galaxy densities. You can see as the galaxy density gets smaller, the void sizes increase, right? So your definition of small and large voids is not general at all, because, well, quasars will have a larger. So we want to find a way to relate this threshold radius that separates small voids from large voids as a function of the galaxy density, right? That is our first step. And to do that, we want to optimize one metric that's called the signal to noise ratio. So this BAO peak signal to noise ratio is basically the height of the BAO peak. You can see in this plot, for instance, that this metric is more or less robust. You can see the correlation functions computed with different thresholds for large spheres. And you can see that it remains well defined, right? And if you check the signal to noise ratio, you'll see that it peaks at some radius. In this case, for instance, for BOS DR11 data, it's 16 megaparsecs per age. So we want to do something similar to this, but in a larger scale, because we will do a grid search not only in the radius code or the threshold radius, but also in the density direction or the density parameter. And we do it for two spheres population, which is the small spheres and the large spheres, defined as this. And we will use also the cross correlations with the galaxy tracers. So the quick summary of that is that, well, here you may see this different signal to noise ratio maps for both of the samples I just talked about and both the correlations I just talked about. So 4 cases in total. We see large voids in the autocorrelation show a very large dependence on the density, and that the fit is very good. However, in the cross correlation, even though the absolute value of the signal to noise ratio is larger, indicating that the signal is a bit better, the fit to the power law is not as good, and it's quite difficult to deal with these really low densities here. So we will stick to the void autocorrelation to select the optimal void radius. On the other hand, the small spheres, we can see that even though fits are quite good, they don't bring much more information to the table, right? The signal to noise ratio is relatively small, and the dependence on the galaxy density is very, very weak, as you can see in these power parameters. So in the end, we just use the void autocorrelation to define this optimal radius cut as a function of the galaxy density. And we check that for BOS densities, the value is pretty much what we would expect or what we found in earlier studies. Now we do that also after reconstructing the boxes, and we find pretty much the same exponent, so minus 0.24, as you can see, but smaller amplitude, which is, well, it makes sense since the reconstruction procedure makes the larger voids smaller and smaller voids a bit larger. So it narrows down the void size function. So in this case, for BOS densities, the radius cut is a bit smaller. So in redshift surveys, what happens is that we can't see the sky uniformly. There's some angular systematics and some radial selection that we have to take into account. So for instance, angular systematics that's caused by bright stars or the atmosphere or some things like that, then that causes you to not be able to see the sky very well, and introduce a small or moderate incompleteness in the angular direction. However, the radial selection introduces a very large incompleteness in the Z or in the redshift direction, in the radial direction. So here you can see, for instance, that there's a very large drop at the edges of the survey, for instance. So if we want to piece all these together, so the void sizes depend very strongly on the tracer density, we have some relation as to the optimal cut as a function of the tracer density. And we know that in surveys we cannot observe the sky uniformly. Then now we have the tools to study how this non-uniformity affects the void clustering, right? So we first simulate the survey incompleteness, both in the angular and in the radial directions. So for the angular plane, which is the XY plane in our cubic simulations, just introduce some parabolic model with relatively high completeness, and then extract voids from there. You can see small voids, as we said before, they trace the overdensities, while the large voids trace the underdensity. And we see pretty much the same if we model the radial selection as a Gaussian bell. So small voids are still bells, and the large voids are sort of bowls or even a bit flat in some bins. So to study this, we will use two different large void samples in this case. One is a constant cut, which is basically what has been done before. So this 10% improvement I've been talking about was with a constant cut. Here you can see basically it doesn't depend on the local galaxy density, right? However, we can take a local cut that depends on the local galaxy density and can help differentiate empty regions from incomplete regions in the survey. So we compare the clustering of these two first in the angular low incompleteness case. You can see that even a small incompleteness introduces some bias in the galaxy-galaxy correlation function. So here for reference, the red curve is without the systematic added, or for the complete sample, uniform sample. But you can see also that for voids, even auto and cross correlation, both of them show that if you use a constant cut, then you see no bias. So the constant cut is actually very robust to these unknown systematics, because here we have not used not even the perfect random catalogs to compute the correlation functions. That is, we have not taken into account for the normalization that the field is actually incomplete. So they are very robust to this small incompleteness. If we use the local cut, however, you find pretty much the same bias we find in the galaxy correlation function. And that is well expected, because this more precise measurement of the correlation function is much more dependent on the normalization we use. If we use the correct normalization, that is, if we know all systematics, then we can recover the correlation from the complete box, which is very, very good. If we move on to radial
3 minutes, Daniel.
Which is, oh, sorry. So here, what we have to see that first, we have to use the correct normalization always. And that if we do so, even using the constant cut, we introduce this strange exclusion peak. But if we use the constant cut, then we can solve this problem. And the issue is that this peak, as you can see here, for instance, from light cones, it may intrude upon the BAO scales, right? And it will make the fitting a bit more difficult. And this is especially true in pre-reconstruction. In post-reconstruction, actually, the reconstruction process already fixes this problem by making large voids smaller. So you can see the signal to noise ratio post-reconstruction doesn't change that much, but before reconstruction, the improvement of using the local cut is very, very significant. So now I'm gonna move a bit faster. I'm gonna show you the BAO measurements from the simulations. And here you can see all the distributions, they're basically just the same. This means that using a constant or a local cut with our data actually doesn't really matter, because the same parameters are recovered, and the red envelope you can see is the fit to the complete box. So actually the parameters are all perfectly recovered in this case. And for light cones, we don't do void only, but the combination of the correlations. And we compare the local in the x-axis with the constant cut in the y-axis. And then you can see that the results, even though, for instance, for BAOs, you may find a small improvement, the bulk of the mocks show that the results are pretty much equivalent. So as a conclusion, or as a bunch of conclusions, we know that first, the void radius does depend a lot on the tracer density, that the constant cut is very robust to small unknown incompleteness, right? Because we don't have to perfectly know the normalization in order to compute unbiased correlation functions. But it happens to induce a large exclusion peak in the void correlation functions towards low scales. Now, we can deal with this either by using a local cut and the correct normalization, or by taking into account these exclusion effects that include this effect. So we conclude that if you use post-reconstruction data, which is, I would say, normal or the standard, then a constant cut may be enough if your data is dense enough as our data. You can imagine that for sparser data, we will have larger and larger voids, and then the use of a local cut may be necessary in that case. And last, well, our group has been done this void analysis for BAOs and EBOS now in a couple of weeks, and we would like to continue with these projects for the DESI year 1 data, hopefully very soon. And thank you very much. That's it.